Welcome. This is going to talk about wireless throttling control and where we are using it at a distillation column at the University of Texas. And we're going to go into more of that. But this is how do we approach and apply PID Plus. And PID Plus started out on really the monitoring side of it. So how do we adapt or start to adapt PID or PID Plus for throttling valves? Because we already have discrete valves. Now we start to look at the throttling side. There's three of us. There's Terry Blevins, Stephen Briggs with the University of Texas, and myself. So at the University of Texas, they've got a divided wall column, and there's a whole separate discussion on that. There's a gal, Bailey, that's doing that and talking in depth about what they're doing with the divided wall column. But as the University of Texas and Bailey are doing that research, they're also working with us using new wireless technology to perform that control. And so we've done tests and they're putting it in process, and she's going to be probably working on it for probably at least the next year doing testing. And so the challenges of a wireless valve is really the challenges of any wireless communication. All wireless communication, even in your cell phone, when you went from a normal landline phone to a cell phone, you notice there is a little bit of latency. And then there's also a thing called jitter, where every time you communicate, it's slightly different than the last time. And so how do we approach PID and overcome or make those differences in communication not matter? And so we did some testing in a lab in Marshalltown, and we're going to kind of go over that. And then we're taking this out to the field in preparation for the actual testing. So PID Plus, made by Terry, came out in 2000, I don't know when it was, but it's since version 11 of Delta V. And what it does is it takes in the non-periodic updates of wireless devices. When you had wired devices, you had a controller that would poll for the inputs on a scheduled update period. Well, in this case, that doesn't happen in a wireless world. In the wireless world, the devices send an update to the gateway. And so the control system doesn't know when the updates are coming in. They just know that they're coming in at a certain rate. Terry worked on the PID algorithm to account for that non-periodic updates, and he's going to go into that. But what we're doing on this side is now looking at the control side. There's that variable time to get that information to that valve, that latency and jitter, and how do we use that. And then we are implementing a new command that we're going to put into the devices in the future that we call time to apply. So what is time to apply is the control system wants to send or know exactly when the device or the valve is going to move. And by doing that, it can run its PID algorithm more effective. And Terry can go into that. But what happens is we have an output from the control system. It hits the valve, and the valve then sends an acknowledgement back to the control system saying, I got the command. And it reaches the valve, but then we don't execute on that command until the future. So he might send it out at time equals 2. We get it at time equals 4, but we don't execute until time equals 6. So the next time, it might take, instead of 1 second to get there, it might take 3 seconds to get there. But then we may not execute it until time equals 6 again. Gets there in time 3, and we execute time 6. The next time, it might not get there until t equals 5, and we execute at t equals 6. Or it might get there at time equals 1, and we execute at time equals 6. So every time we're going to execute at that scheduled period that the PID algorithm expects and needs. And so what we did was we tested in a lab we have in Marshalltown. We can take the lab and rearrange it and reconfigure it to whatever we want. In this case, we wanted to do some flow loop testing. And so we have different pumps to drive the pressures we need. You can have 2-inch lines, 4-inch lines, which simulates the real process out there. And when we have various valves out there with the trim size and the capacity size to match what we need to do a testing. And then when we do the testing, there are a couple of ways we do that. One is you make a set point change and you watch a response in the process. The other one is you have a set point and you have a disturbance, like with a downstream load valve. You introduce disturbances and see how well the PID control responds to those disturbances. And so we did all of that. That's what Terry came up, and they spent a long time, almost an entire week, doing a lot of different tests with both wired and wireless to figure out how this is going to take place.
Thanks, Kurtis. It's great that you're here today. I know this is being the last presentation on the last day. It's great that you took the time to come today, so appreciate that. This effort on terms of control using wireless throttling valves is really a multi-division effort. Rosemont, the people in Austin that work there, as well as Fisher Control. So it's really a great joint effort to look at the technology and see what's required. And as Kurtis was saying, we've done some pretty extensive testing in the flow lab in Marshalltown. It's just a wonderful facility to try out and prove out on a fairly large scale these techniques. On everything we do, we pretty well test it and prove things out in a simulation environment, but there's nothing like having the real thing to prove out ideas. So as Kurtis was saying, we're trying this new command. Now, this new command isn't supported by the Delta V system or the gateway or the device, but we had the luxury of being able to change all of those since we're all working together. And so we could implement this new command. At the module level, when we changed the output of the AO block, then that's sent out using this new command where we've specified a certain time to apply in the future. And as a result of knowing that we know precisely when the valve is going to change in the future, then we turn on external reset in the PID using the dynamic reset limiting parameter of the block. And then you account for the delay in getting to the valve in this feedback path. And that accounting for the delay and the implementation of this command eventually will either be in the gateway or it'll be embedded in the I/O subsystem. But in our field trial, we actually had to put in something in here to account for the delay. But knowing precisely that it was going to be 8 seconds in the future, then we could precisely delay that by 8 seconds, and then this signal then represented the true valve position. And it turns out then that we could use that with our PID Plus, which may be dealing with a wireless measurement here. So we wanted to test this new command in combination with PID Plus for our testing. We wanted to test both with wired and wireless input, wired or wireless output. And so in the actual installation there in Marshalltown, we created a switch box, we called it. The gateway would be sending out a command to a modified 4320. So that was using this new command. And the 4320 was designed that it would provide a 4 to 20 milliamp output that would go to the valve if the position was in wireless. If it wasn't in wireless, we still sent out a command, but it was ignored here in terms of that value. And we then used just an output, 4 to 20 milliamp output that was going to the valve. So we could test with wired or wireless truly without any real problem. And same thing on the measurement, we were using micromotion, but we had a thumb, and so in the actual module you could just flip between I want wireless measurement or wired. And so as you can see here, we wanted to test all combinations of those working together. This is sort of the baseline test. So what we wanted to do was show that using PID plus and using this time to apply command, you didn't really have to be any specialist. That is, it didn't require special knowledge. And so with wired input, wired output, we actually tuned the control, the PID algorithm, using the on-demand tuning in delta V. So nothing special there. And then when we started using wireless input, wireless output, we never touched the tuning. Because the way PID plus is designed, you only adjust your tuning based on your process dynamics. It doesn't matter how often or how frequently it's being updated in the wireless measurement. And so we wanted to show that as well. So this is the kind of performance that you got with a wired input and a wired output. You notice there's a little bit of an overshoot of the valve there, so it's tuned a little bit hot, but good control over that range. And that's for a set point change, and as Kurtis was saying, we had it set up where we could also introduce a disturbance in it and also observe that. In this case then, we flipped our switch, went to the wireless valve with a wired transmitter. And you notice here that there is some delay in terms of that time to apply having an impact here, but you notice it's very stable. You come to set point in all cases. Not that much different than what you had with the actual wired valve. This is for wireless valve and wired transmitter, where we're introducing a unmeasured disturbance through that load valve up and down. And so that means we then develop an error here when the valve downstream changes, and then the throttling valve then has to be adjusted. But again, you notice it always recovers quite well. No oscillation, no hunting on that. And in this case, in both of these, we're using like an 8-second time to apply. So we wanted to change the valve, and 8 seconds from then it was actually being applied. But we knew about that, and so in the PID we could exactly compensate for that. Okay, so this was with our wireless valve, and now then we're using a wireless transmitter, where the wireless transmitter update rate was 8 seconds. And again, we didn't touch the tuning. It's the tuning that we had established for the wired input, wired output. And now then you notice that it's the combination of that time to apply giving us a little bit of delay in terms of it. But you notice it's absolutely solid, come to set point, no offset, no hunting when you use the two together there. So that's the combination then of PID plus this new technique. And here's the disturbance input changing. And that's for a wireless valve, wireless transmitter. And again, you see it always brings it back. Good, stable control there. And, you know, the control is quite good given the limitations of the delay down and the slow update rate. So I think in a lot of applications, this control is going to be quite effective. We tell people that if you have a need to instantaneously respond to disturbance, you shouldn't really use wireless, right? Not a good application. But I think a good 70% of our loops aren't characterized that way, and so it does a good job for those, I think. So anyway, hopefully this gives you a little glance at what we did there. Now, in the book, we have a whole chapter on this wireless valve control. And we go through something like, I think, 15 different tests that we did. And so you can see all combinations. And since the topic was wireless valve, I don't really show a lot on the other, but the book really shows everything. So if you're interested, want more detail, then would advise getting a copy of the book there. So, but hopefully this gives you a little bit of flavor for what we did and really the benefit of this new command and how it's applied and controlled. So with that, I'll turn it over to Stephen, and we're working closely with UT and actually applying this in a fairly critical process.
My name is Steve Briggs. I work for the University of Texas at Austin as a technical staff assistant level 5, which means jack of most trades, master of a few. I'm going to ask that we refrain from any college football talk, as that is a very sensitive subject in Austin, Texas at the moment. Yeah, what it says, the Separations Research Program was formed in 1984 as a collaboration between industry and academia. Our main focus is to study classical chemical separations processes, mostly gas-liquid and liquid-liquid separations. That includes distillation, absorption, extraction, membrane separation. Here what you see is a picture of our outside process unit. Right here is our newly installed 6-inch diameter divided wall distillation column. And I'll go ahead and point out some of the other equipment we have. Back, it's a little difficult to see in the picture. We have an 18-inch diameter conventional distillation column, which also serves as a stripper. Here we have, back behind this, almost a carbon copy of the distillation tower, is an 18-inch diameter absorber, which can also be used as a liquid-liquid extractor. Down on the ground here, this is a advanced single-stage flash stripper. Here we see a plastic 18-inch diameter air-water column that we use to evaluate mass transfer internals for different devices. Hydraulics, we can get KLAs, KGAs, direct measurements. That's pretty much it outside, as well as all this equipment outside. Inside, we have various skid-mounted and benchtop units available for, a 4-inch diameter glass liquid-liquid extractor. I have a number of different Oldershaw distillation towers that I'm using a couple of times a year. One of the things that sets the university apart, or at least the separations research apart from other academic programs, is our program is staffed by full-time individuals. We actually have a fairly light staff. We consist of a program head, technical director, process engineer, mechanic, myself, and one instrument and controls electrician, and that's it. We do nothing but operate, build, maintain. We pretty much do it all, and every one of us knows how to operate a broom as well. Here is a picture of the unit in question. What we see is the divided wall distillation column is actually broken up into 4 main vessel courses. Classical stripping section. We have 2 actual divided wall beds, 1 rectifying section. We'll start off with the feed and we'll trace the flow path. The ABC feed, or the 3 components, we're going to be using a ternary or 3-component distillation. ABC feed goes through a feed pump, feed flow control valve, feed preheater. It enters this side of what we call the pre-fractionation side of the divided wall bed. Down here we have the reboiler. It's a kettle type reboiler with the steam flow control valve. We monitor direct heat input using the calorimetric equation, measuring steam flow and condensate parameters. As vapor rises up through stripping section, both sections, and into the rectifying section, all the liquid is condensed. A portion of it is returned to the top of the rectifying section as reflux. The remainder of it is withdrawn. This product will be concentrated in the A product. Underneath we have a total trap tray that catches all of the liquid coming out of the packing from the rectifying bed, sends it to a collection tank whereby a pump pumps it back up to 2 streams, basically where we feed both sides of the divided wall bed independently of each other. Down here is where we take the B product, or the intermediate product, down to a tank controlling level, send a portion of the B product back to as B product reflux, and then take the rest of it out back to the feed tank as B product. And right here is just a conventional bottoms liquid stream. Now, how we're going to control this, this is one of the things that's going to be extremely challenging for this application because of our tiny scales, large surface to volume ratios, and the fact that centrifugal pumps on this scale are generally not readily commercially available. We are locked into pretty much using gear drive positive displacement pumps. You can see what we're doing here is downstream after it's preheated, we're actually splitting two parallel flows off of the discharge of a gear drive positive displacement pump. I don't think it's shown in the drawing, but we are using a trick. We're using a back pressure regulator to take the excess flow back to the tank to kind of trick the pump into thinking it's a centrifugal pump. The basic control scheme, this is the top of the divided wall bed, and you can see here we're actually feeding both sides of the bed independently of each other. The the controlled variable is going to be the temperature in the bed, which will be inferring composition, and that's what we're going to try to control. Going to send a signal to a flow ratio controller, which is going to be cascaded to a flow controller slaved off of. It's actually a drum level. This is not shown. There's a drum where all the liquid is being pumped into. As you can also see here, there's a temperature controller here, controlling steam flow to a preheater. The next loop, this is the B product loop. Very similar. We're actually measuring temperatures that are inferring composition, sending it to a cascade flow controller, which is driven off a level controller, as well as a preheater and a distillate flow control. The final installation, this is what it looks like. What you see here is 1, 2, 3, 4 flow control loops, 1, 2, 3, 4 micromotion Coriolis mass flow meters, 2 steam flow control valves, 2 heat exchangers plus steam traps, and a wireless 848. This little skid is approximately 0.3 meters by 2.4 meters or 8 foot long, 1.5 foot wide. So there's a whole lot of instruments in a very, very small package. And as well, you can see the wireless thumb adapters on top of all the micromotions. Again, we pretty much just finished assembling. We're just finished gross leak checking. We're now in the process of acoustic emissions testing as soon as I get back. And this month, we will be charging with chemical and conducting experiments.
Thanks. Yeah, as you can see, it's a really interesting process. There was a whole nother workshop just where we talked about the process and some of that upper loop, the temperature control. And we'll be using MPC with wireless on that. But at the lower level then we'll be using wireless for the 2 temperature control loops and for the 4 liquid flow loops. So we're talking about really fast processes and then fairly fast process with the temperature. And then for the actual composition, very slow process. So we'll be showing and demonstrating a whole mixture of dynamics and application using wireless. And like Steve was talking about, we can flip between wireless or wired on the valve or the measurement on any of these. So we can prove out all combinations. We had hoped to be able to present the results of this here, but shipment of the column due to fabrication and that was delayed by over a month, and so it sort of shifted everyone's schedule and we didn't quite make it. But like Steve's saying, you know, within the next month or so this will all start to come online. So it'll be a interesting project, and next year we hope to be able to present the results. We think they'll pretty well match what we've done. We have a complete simulation, dynamic simulation, that we used in testing all this. And so hopefully we'll match what we're doing with the simulation and the real live thing. And I'm sure we'll learn a few things that didn't show up in the simulation. So so it'll be a good test and good learning experience here. But with this approach in terms of wireless. There are a lot of benefits, and Bailey talked about that in this other session. So in terms of the installation and ease of changing things around, especially in this kind of an environment. There's some papers that we've written on some of this, and really most of what those papers talk about are more than covered in the book as well. The book itself is available on the ISA website. We're going to be turning it into an e-book, so hopefully pretty soon you'll be able to get it as an e-book. And pretty soon you'll be able to get it on Amazon as well. So anyway, we hope the book will be of help to you. There's a website that goes with the book called Wireless Control Foundation, all one word. If you go to the website, there are 10-minute YouTube videos on each of the chapters of the book. So if you wanted to go back and show someone wireless control or wireless control with a valve, well, there's a video on that, and you can actually show them the dynamic response that's shown in the video. And so we hope this will be helpful to you. If you want to give a presentation on wireless control, if you go to the website under the book, you'll find that there's a PowerPoint presentation on each chapter that captures most of the actual graphics from the book and a lot of the words. And so you can give a PowerPoint presentation on wireless control. So anyway, so we hope these tools will be helpful to you in looking at it within your own organization and selling the idea of using wireless control. We'd like to thank you for coming.